Chapter 5, Section 3 is about function rules, tables, and graphs. So by the end of this lesson, you should be able to model functions using rules, tables, and graphs. Two new vocab words for us, continuous and discrete. Continuous data is data where the numbers in between two data points have meaning, and discrete is data where numbers in between two data points do not have meaning, so things are counted. So you can model functions using rules, tables, and graphs. A function rule shows how the variables are related. A table identifies specific input and output values. A graph gives us a visual picture. So remember from 1.4 that inputs are independent variable stuff and outputs are dependent variable stuff. So when we go to graph things, we have our x-axis and our y-axis. The x-axis is where we graph the independent variable. The y-axis is where we graph the dependent variable, so that's why we have points x, comma, y. Your input-output values are ordered pairs. So this 3, 2 here means I plugged 3 in and I got 2 out. And then we join the points with a line or a smooth curve to give a general picture of the function. So for this one, we plotted 3 points. And we could see they were all in a line, so we drew a nice line through it. So model the rule f of x equals 3x plus 4 with a table of values and a graph. So we need to make ourselves a table of inputs and outputs. So you could write f of x or you could write y. It doesn't really matter. This is what we're plugging in. This is what we're getting out. And then just pick some of your favorite numbers. So let's do some negatives, like maybe -2, -1. Let's try 0 is a good one, and then some positives. And then just plug these in. If you do 3 times -2 and add 4, we get -6 plus 4 gives me a -2. If I plug in -1, I get -3 plus 4 gives me +1. If I plug in 0, this is a nice easy one, I get 0 plus 4, which is 4. Plug in 1, 3 plus 4 will give me 7. And then finally I can plug in 2, and I get 6 plus 4, or 10. So this right here is actually a table full of points, inputs and outputs. And because of that, I can go through and plot these points and make a graph. So my first one, I went back 2, down 2. Next one, back 1, up 1. Next one, I go up 4, 7, and finally up 10. And because my graph isn't nice and perfect, this line isn't nice and perfect, but we can kind of see that these form a nice pretty line. So we modeled it with a table over here and a graph over here. So back to that continuous and discrete. So remember, continuous means that I can take points and connect them with a line because everybody in here still has meaning. Discrete data, I just would plot points because it wouldn't make sense to have anything in between. So determine whether the function rule models discrete or continuous data, then make a table and graph the function. We're going to skip this part and just figure out if it models discrete or continuous data. So an automatic photo booth charges $3 for a sheet of photos. The function C of P equals 3P describes the cost of P sheets of photos. So if we thought about this and did make a table, plug in numbers for P, get things out, like let's say we bought 1 sheet, it would be $3. 2 sheets would be $6. 3 sheets would be $9. Does it make sense to have data points in between here? Like, does it make sense to have 1.5? We can still plug it in here. We'd get 4.5, but does that make sense with our problem? So because P talks about sheets of photos, we can't buy half a sheet of photos. So even though like $4.50 makes sense, it doesn't make sense with the problem. So this would be discrete. If I wanted to graph this, I would just graph points. I would not connect them. Now the next one, the function of m of w is 1/6 w, describes your weight on the moon as a function of your weight on Earth, w, which is in pounds. So we have w, which is our weight in pounds, and then m of w, which is our weight on the moon. And let's say I weigh 100 pounds. I could take 1/6 of it and get 16.7 pounds on the moon. Or let's say I weigh 200 pounds. I could take 1/6 of that and get 33.4 pounds on the moon. Now, does it make sense to have values in between here? Well, of course, nobody weighs exactly those two things, or not everyone does, so there's got to be some people in between. So this is continuous, and if we were to graph this, we could plot the points that we have, but we would want to connect them with a line, because it makes sense anywhere in between here. And even if we went through and listed like 100, 101, 102, somebody can weigh 102.5 or 102.25. So continuous means that everybody in between still makes sense with the problem that we have. So some functions have graphs that are not straight lines. You can still graph any function as long as you know its rule. After you've graphed ordered pairs that you've calculated from a rule, you join points with a smooth line or curve. So let's graph these two things. Make a table of values and graph each function. So I'm going to have x's and f of x's. And for both of these, let's use those same x values that we plugged in before. Now this first one says I have the absolute value of -2 and then take away 1. The absolute value of -2 is 2. Minus 1 gives me 1. Do the same thing for -1, take the absolute value and then subtract 1. Remember, absolute value talks about distance, so -1 is 1 space away from 0. If I subtract 1, I get 0. If I do the absolute value of 0, it's 0 spaces away from 0. Minus 1 gives me -1. Absolute value of 1 is 1. And if I take away 1, I get another 0. Then finally, I have the absolute value of 2, which is 2. Minus 1 gives me 1. So I, again, have just made ordered pairs here. So I can plot them. Back to up 1, -1, 0. I have 0, -1, 1, 0, and then 2, 1. And from this, we can see that this curve has a nice sharp point, and it goes off in either direction. This is an absolute value graph. If ever you have absolute value bars, you know you're going to draw a V-shaped graph. Now let's try the next one. It looks very similar, except it has an x squared. But still, let's make our x and our y's and plug stuff in. Let's use the same points. So if I plug in -2 and square it, I get 4. Minus 1 gives me 3. If I plug in -1 and square it gives me 1. Minus 1 is 0. If I plug in 0 and square it, I get 0. Minus 1 is -1. And then I plug in 1. 1 squared is just 1. Minus 1 is 0 again. And then if I plug in 2 squared, I get 4. Minus 1 is 3. So I go back 2, up 3, back 1, 0, down here, here, and here. Now this one looks a little different than the other one. This one had the same kind of slope on each side, went up and over. This one does not. This one goes up and over 1, but then it jumps up. And because of that, we're going to have to draw it as a nice smooth U. This is a parabola. Anytime you have an x squared, you're going to draw a U-shaped graph. So you need to keep those two things in mind. Absolute values mean V's. X squared are parabolas. They mean U's. So you should be able to model functions using rules, tables, and graphs. You need to do number 39 right here for your Can You Prove It? Make sure you write down any questions if you have them, and we can go over them in class tomorrow. Have a good night.